Hello learners, welcome to this course on practical machine learning using Google Colab. In this tutorial, I will be discussing about how to perform a handwritten digit recognition using neural networks. So handwritten digit recognition, we are going to make use of a MNIST dataset. So MNIST dataset, it contains about 60,000 training images and 10,000 test images. So let me show some image data from MNIST dataset. So if you look at, it will contain images like this. It contains handwritten digits, images which are grayscale in nature. So, and the size of the images is going to be 28 by 28. So, width is 28, height is also 28. So, we will have about 28 by 28, which is 784 pixels in an image. So, important thing to note here is this MNIST dataset is pre-processed dataset, which means the digits are at the center, noise is removed, and it is aligned properly in an image. So when you try to do it on your own handwritten data, so you need to do some pre-processing such that the handwritten digit should be at the center and any noises should be removed and the digit should be in a grayscale value and the background should be in a black color. So like this, if you have created your own handwritten digit image, that you can test it on this network. So the important characteristics of this data set is each image is grayscale in nature, which means the pixel value vary from 0 to 255 and the size of the image is 28 by 28. So we are going to use this handwritten digit for our neural network prediction. So first let us import the packages which are required for our application. So I am going to import a NumPy package, which is a numerical Python library which is mainly used for array or matrix computation. Then we have MNIST dataset from our Keras package. So Keras is an advanced machine learning library, so through which I am going to download this MNIST dataset. Since we are going to create a neural network which is sequential in nature, it has an input layer, hidden layers, output layer, which comes in a sequential fashion. So we import a sequential model from a Keras package. And since earlier layer neurons provide the input to the subsequent layer neurons, we say it as a dense network. All the earlier layer neurons provide data to the current layer neurons. So which is called as a dense layer that we try to import again using a Keras package. We can also induce some dropout of some neurons during the iteration process. So this dropout can be in terms of a 20% dropout or 30% dropout. It can be varied, which means randomly, for example, if the dropout of 20% is introduced, so randomly 20% of the neurons will be removed while updating the parameters. So this 20% neurons which is being removed from the network, it varies from epoch to epoch. So that layer is also updated from the Keras package. And we can make use of the utils available in the Keras package to perform one hot encoding method for the labels. So the labels, handwritten digit labels, it will be from 0 to 9. This can be converted into a vector form using a one hot encoding method. Then from sklearn package, we can import the classification report to see our performance metrics like precision, recall, F1 score. So these are the packages which we need to import into our program. First, let us get connected to the Google Colab environment by pressing this connect button. It gets connected to the cloud environment. It gets initialized and the status says connected. Once it is done, we try to import or run our cells in the Google Colab environment. First, let us run the package cell. It is getting imported to our Google Colab environment. Then, what we do, we initialize a seed value. So, this seed value is required for proper reproducibility of the results. So, while picking the data set, we need to pick the appropriate images or data. So that can be done with the help of this random seed function. Once this is done, we can import the data set from Keras package using this function MNIST.load_data. So thereby I get training data and its labels, same with test data and its labels. So here training data and training labels will be 60,000 in number. Test data and the test labels will be 10,000 in number. So we try to download that data. Once it is done, we try to see the shape of the data. So here the shape will be in this format. I will have height, width and number of samples. So this is something like a one-dimensional array. So in position 0, I will have number of samples. In position 1, I will have width information. And position 2, I will have height information. So we print the length of the training labels and length of the test labels. So we know the length of the training labels will be 60,000. Length of the test labels will be 10,000. By using a dot shape function of 0, I get the sample information, how many samples are there in the training data. Same way, dot shape of 1 will give me the width information of our training data. Shape of 2 will give me the height information of the training data. So here the width and height are 28 by 28. Same way for the test image also, I can check using the dot shape of 0, shape of 1 and shape of 2. So I will get 10,000, 28 by 28. So when I run this, you can see training data is going to be 60,000 in number, test data is 10,000 in number, and the shape function returns the samples, width, height, and the training data, test data samples. So now let us reshape our data. So in order to reshape the data, I need to find the number of pixels in the image. So that is done by this dot shape of 1 will give me the width information of the training data. Dot shape of 2 will give me the height information of the training data. So width into height, it gives the number of pixels. So 28 by 28, it comes to be 784 pixels. Then using this value, I am going to reshape our training data. Using the dot reshape function, I give the number of samples in the training data, comma, number of pixels. So 60,000, comma, 784. Same way for test data also, we reshape the data, 10,000, comma, 784. So when I plot it and see, you will get dot shape of 0 will give me the sample information and dot shape of 1 will give me your number of pixels, 784. You can see 60,000 and 784. Now we can normalize our input data by dividing the training data by 255. So 255 is the maximum grayscale value in our image. So our image contains a pixel value from 0 to 255. So we divide the training data by the maximum value to get a value between 0 to 1. Same way, the test data is also divided by the maximum value to get the value between 0 to 1. So we try to normalize our input data. Once we have normalized our input data, we need to work on our labels. So labels for each image will be in terms of 0 to 9. So this labels should be converted into a vector for further processing. So for that we make use of a technique called as one-hot encoding method. So one-hot encoding method is very simple. So here I have the labels associated with the data which varies from 0 to 9. So depending upon the label of the image, I create a vector. So we put an associated value for each label. So if the first image contains digit 0, then the bit associated with digit 0 is set to 1. Other bits associated with other labels are set to 0. Same way, if the image contains a digit 7, then the bit associated with the digit 7 is set to 1. All the class bits are set to 0. So like this, we convert our label in the form of a vectors. So that is done by this nputils function, nputils library package. So in nputils library package, I have a function called as to_categorical. So I give the training labels and test labels to convert it into a vector format. So here, in order to get the number of classes in our data set, we use dot shape of 1, which gives the width information. So width information provides the number of classes. So that we try to get it using the dot shape of 1 function. So that comes to be 10, and we try to print it and see. So once this is done, we define our base neural network model by defining a function. So baseline model. So we are going to use a sequential network. So I initialize the model with the sequential class. Then I use a hidden layer declaration. So for hidden layer declaration, I am going to add a layer to the model, which is a dense layer. Dense layer means all the previous layer neurons is going to contribute to the neurons of the current layer. So how many neurons I should have in my hidden layer? I am going to take number of pixels. So number of pixels is 784. So our hidden layer is going to contain 784 neurons. How many inputs are going to be obtained for the neurons? That is specified here. Input dimension, I am going to take it as 784. Right? Because our input image is 28 by 28. So our input dimension is also 784. So we have number of neurons in the hidden layer is also 784. The inputs to the neuron is also 784. So for initializing the parameters, so we have weights and biases which needs to be initialized. So this initialization can happen using a random initialization or from some distribution. So here I am going to use the initialization which is from a normal distribution. From a normal distribution, we assign the weights and biases. And the activation function which I am going to use in the hidden layer neurons is ReLU activation function. So ReLU activation function means for a negative value of x, we will have the output of the function to be 0. For the positive value of x, we will have the same value as the output. So after defining the hidden layer, I am going to define an output layer. Again, we use a model.add function to add a layer to the network, and I say it is a dense layer. And the output layer, the number of neurons depends upon the number of classes. So here we have already seen I have number of classes to be 10. So I define it here, the number of neurons in the output layer as number of classes. Again, we need to initialize the parameters, weights and biases. I use a normal distribution for assigning the weights. And since it is a multi-class problem, so multi-class in the sense I have 10 different classes, I use an activation function which is softmax in the output layer. So softmax will try to provide a probability score for each and every class. Then we try to take the class with the highest probability, and that label will be assigned to that input data. So once our model is created, we need to define some more parameters to the model. So that is done by using this model.compile function. So here the first parameter which we are going to define is the loss function. Since it is a multi-class model, we use a categorical cross entropy loss function. Then how the weights should be updated during the back propagation phase, how the weights and biases needs to be updated. So we have different types of optimizers available like ADAM, ADA Delta, ADA Max, SGD, etc. So here for this we are going to use the ADAM optimizer. And the metric to update our parameters is accuracy. Based upon the accuracy, our model parameters are going to get updated. So that completes the definition of our model. So first we create a model, then we set the parameters for the model. So now let us use this function to create our actual model. So that is done by this. First we initialize our model to be a baseline model. Then we define the summary of the model. We create a model. So first let us run this function. Then create a model. When I run this model, you can see the model summary. So the model summary states that I have two dense layers. So one layer is a hidden layer and another layer is an output layer. So let us take the hidden layer. So in the hidden layer, my output shape is none, 784. So 784 defines, since I have 784 neurons in this hidden layer, I will get 784 outputs from this hidden layer. How to define this parameter? So I have 784 neurons in the hidden layer, and this 784 neurons gets input from the input layer. Again, the inputs is 784, which is nothing but 28 by 28. Image size, it gets converted into 784. So the number of neurons in the hidden layer is 784, and I have 784 inputs. So how many weights I will have? I will have 784 by 784 weights in the hidden layer neurons. And this is added with the bias term. So 784 biases. For each neuron, I will have a bias term. So I have 784 bias term. So totally when I sum it up, you will get 615440 parameters in the hidden layer. Same way for an output layer, what will be the output shape? We have 10 classes, so 10 neurons are there, so our output will be 10. How many parameters? I have 10 neurons in the output layer. So this 10 neurons gets inputs from the 784 neurons in the hidden layer. So which is nothing but the number of weight is 784 into 10 plus 10 bias term associated with the neurons in the output layer. So altogether you will get 7850 parameters in the output layer. If I add, I will get the total number of parameters of our network. So this many number of parameters should be optimized to get a better accuracy. Once our model is defined, we need to do the training process. For performing the training process, we use a function called as model.fit. So model.fit, I give the training data, training labels. In validation data, I give the test data and test labels. So after every epoch, we give the test data to see how the network is performing for every epoch. I am going to run this model for 10 epochs with a batch size of 32, which means the weight updation happens for every 32 images. So it is called as a mini batch. So mini batch updation. For every mini batch, the weight gets updated. And verbose 2 is for defining how to see the output. We have different something like verbose value 0 means we will not get intermediate results, whereas verbose 1 means we can see a progress bar, 2 means we can see for every epoch, one line will get printed. So when I run the training of the model, you can see first for epoch 1, it is getting executed. You can see I have a loss. So this is the training loss, training accuracy, validation loss, and validation accuracy. Let us wait for the training to be completed. So now it is running for different epochs 1 to 10. Since we are running the training for 10 epochs. So for each epoch, it produces a training loss, training accuracy, and validation loss and validation accuracy. And here it specifies how much time it took for each epoch. And what is the step size? How much time it took for each step. So now the training process is complete. Here you can see I have 1875 is the number of batches in our training data. So if I take a training data is about 60,000 images. So our batch size is 32. So 60,000 divided by 32, it comes about to be 1875. So this many number of batches are available for each epoch. For each epoch, we obtain the training loss, training accuracy, validation loss, and validation accuracy. So if we closely look at this training loss and validation loss, we can identify whether our model is overfitted or it is underfitted. So we get a very good accuracy. You can see I can get an accuracy of about 99% almost. In validation, I can get about 97%. So which means it is not underfitting. Right? We need to check whether our model is overfitting. For doing that, we need to see the loss variation with respect to epoch. When I try to see the training loss, you can see the loss gets decreased as the number of epochs is increased. You can see first initially it started with 0.1881. It reached after 10 epochs 0.0102. So the training loss got decreased. When we look at the validation loss, what happens? Initially the loss was 0.109. So it slowly started decreasing. Once it reaches this point, if you see, after this point 0.0693, it started increasing. The loss started increasing, which means it had a dip and then it starts increasing. So our validation loss kept on increasing after this point, after epoch 2. So which means our model has started overfitting. So we need to stop our model at epoch 2, because after this our performance gets poorer and poorer. Okay, it is not going to give a better accuracy. So we need to stop at this point. So we can use some early stopping condition to identify how this validation loss varies. If there is not any improvement in the validation loss, we can stop our training process, thereby avoiding our overfitting of the model. So by this method, we can identify whether our model is overfitting or underfitting. So once our training is done, we can evaluate our model by providing the test data and the test labels. We can get the score and we can print the accuracy of the model. So here you see an accuracy of about 97.94% is obtained. Remember, this is after 10 epochs. But if I want a better performance, I should stop at epoch number 2, because after epoch number 2, our loss, validation loss gets increased. So now let us put a classification report so that we will see the precision value, recall and F1 score, which are the other performance metrics. So in order to do that, I use a model.predict function. I give the test data, make the predictions. So while making a prediction, we will get two things. One is for a particular sample, what is the prediction? So sample number 1, what is the prediction? Sample number 2, what is the prediction? Sample number 3, what is the prediction? So we will get the data in terms of an axis. In axis 0, I will get the sample. In axis 1, I will get the predictions. So we try to see the prediction. So prediction is along the axis 1. So I take the maximum of the prediction, because since I have used a softmax activation function, we will get a probability score. So I will get a score for each class. So I need to take the maximum of that score. I need to identify the class with highest probability score. So that is done by this np.argumentmax. So then I will try to assign that label as a prediction. Then use that prediction to print our classification report by comparing it with the ground truth value. So when we run this, we can see the performance metrics. So this is precision, recall, F1 score for each class. For 0, precision is about 97%. For class 3, it is 98%. For class 8, 98%. It goes on. So from this, we can understand our model really performs well. We can get a performance metrics in terms of 97% to 99%. So it is a very good model prediction. So that is how we run a handwritten digit recognition using a neural networks. So here in the performance metrics, we get a support value which indicates how many images are with digit 0 in the test data. Same way, how many images are with digit 7 in the test data. So that is given by the support. So if I add all these values, I will get 10,000 test images. So in this tutorial, I have discussed about how to use a neural network for making handwritten digit recognition in a Google Colab environment. So thanks for watching. Please subscribe for more technical learning. Thank you.